Hello, and welcome to another session on Feedback Control Lab. So today we would like to simulate uh, the response of this linear ordinary differential equation. Okay, so we're going to use different methods to simulate the response of this differential equation. As you can see, this is a second order differential equation, and the first method that I'm going to use is that I'm going to use the Laplace operator. So let us first of all obtain the transfer function of this system, and then I guess we can start from there. Okay. Okay, so I want to obtain the transfer function. So the first thing that I do is that I'm going to apply the Laplace operator to this both side of this differential equation. So doing so, I will obtain y of s, and in parentheses, I would have s squared plus 3s plus 2 equals to u of s. Now, the definition of a transfer function, as you guys know, the transfer function will be defined as the Laplace of output. In this case, the output is y, divided by a Laplace of input, which is u. So the transfer function is simply 1 over s squared plus 3s plus 2. Okay, so now if we want to obtain the, let's say, the response of this system into a step, what we need to do is that we define the input u as a step function. In this case, its Laplace is 1 over s. Okay, and then the output y would be just this transfer function. Let's call it for now g. Okay, this is g of s. Um, would be g of s times u. Okay, so now this would be the response of a system in the Laplace domain, and we can obtain the response of a system in the time domain by taking the inverse Laplace of this transfer function, and this is actually the response in time domain, but we're going to write a simple code in MATLAB to perform the same thing. Okay, so let's get to the MATLAB. Now, let me save this code as an example. I'm gonna call it probably example line. Okay. Now, in this system, I use a symbolic mass, and I define two symbolic variable, s and t. Then I defined my transfer function, g, as 1 over s squared plus 3s plus 2. And then the input to the system, in this case, is for the step. So the Laplace of a step function is 1 over s. And finally, the output of this system is just the transfer function times input. And then I define the inverse Laplace of y to obtain the time domain function. So let me just go ahead and run this code. I'm going to change the folder, and Let's take a look at a workspace. And matter of fact, it's a good practice that I beforehand I put this line to clear the workspace as well here. And let me run it one more time. And this is the output of this system in the time. Now, one thing that you got to pay attention is that this is the output, the exact analytical solution, and is based on these symbolic variables. So one way to simulate this now is that I can define a time vector. Okay, let's say I define time equals to from 0 all the way to let's say 10 seconds. And then I define a for loop for equals to 1 all the way to length of my time vector. Okay. Let's obtain the output, which in this case I introduce it as y equals to. Now let's use the subs function in MATLAB, and then we're gonna have our output y, and let's substitute the variable t with time, increment of time, and then that should be it. And then we can plot time versus double y, and this should be the response of the system for this period of time. Let me just quickly run this and see if it works the way we want. Okay, so this is the response of a step response of this system. And as you can see, we were able to use symbolic toolbox and exact analytical solution and obtain this graph. Alternatively, what I can do is that I can actually get this analytical solution that I have, and I can just write another code where I define my time vector as for 10 seconds, a vector for 10 seconds, and then the output y can be this function. Now, let's see if it's gonna run. Probably these are gonna be a vector, and then it may not be able to add a scalar value to the vector, or it may add. I'm not sure 100%, but let's just run it and see if it's gonna work or gives us an error. So it worked. I mean, but in some cases, because this time is a vector and then this is an scalar, it just added to this vector to all the elements. But if there was an issue, you can always add multiply this constant with a vector of 1 with the same size of t. So it will get rid of the error. Anyway, so this is yet another way to simulate that if you don't want to use the subs here. And you can even write a function by introducing these to simulate it. But there is another way also to do the same simulation, and that is by using the lsim command in MATLAB. And for doing that, I'm gonna just do this. I'm gonna add this thing here. I'm gonna introduce s as a transfer function of s. And now I define this g as my transfer function. You got to pay attention that this is not a symbolic variable here, and g is a transfer function. Now we have this command in MATLAB. Let me call this guy y1, and then I can call y2 uh, equals to lsim. So this is for linear simulation of the transfer function, and it received 3 arguments. The first one is the transfer function, the second one is the input, and the third one is the time vector. Now we haven't yet defined the input. Let me go ahead and define that. For the case of step, let me define u as one's size of t. So it's gonna u gonna be the input as a step because ones is a vector with all the elements 1. And then this is my first plot, and then let's have another plot. This time gonna be this y2, and let me use the hold on. So we're making sure we're not missing this one. And then let's use some sort of character so we distinguish the difference between these two. Let me save this one here as well, and maybe we call it example transfer function. Okay, let's run this. Okay, so these two lines are on top of each other. Actually, let me reduce the step size here so you can clearly see that these are actually on top of each other. Okay, I can see, you can see the solid line, the blue line is for the first method based on the analytical, and then here I'm using this solver for linear system in MATLAB, and these are identical solution right now. So we use the symbolic toolbox, and we use the LSIM to simulate this linear differential equation. Um, Alternatively, what I can do is that I can use the find the difference method to simulate the same differential equation. Now, if we get back here, let me clear these things from here, and I can explain how we can now use find a difference to solve this equation. So the idea here is that we can actually estimate the derivatives with this finite difference equation here. So if I want to solve this differential equation, the first thing that I'm gonna do is that I'm gonna organize it and solve it for y double dot. This is the first line that I did here. And the second thing that I'm gonna do is that I'm gonna approximate the first derivative of y dot, based on y double dot. And also I'm gonna approximate y based on the first derivative. And these are all coming from the definition of a derivative, and or you can think of it as like approximation using the Euler series. Now here you can have a second order term adding here to make it more accurate, but for sake of this example, I just stick with first order elements. Now, what I'm going to do here is that these sets of equation, I'm going to write it down in a way which is more appropriate for coding. Okay, and essentially, I'm going to substitute t with I and t plus delta t with I plus 1. So I'm going to rewrite this equation. And by the way, in my handwriting, I prefer to show if I have a second derivative, y double dot, I usually show it with double d y. You may have different notation, that is perfectly fine. And if I have y dot, I'm gonna show it v dy when I do the coding, I mean. So knowing that, then I'm gonna rewrite this first equation as double d y of I equals to u of I, okay, minus 3 y, actually dy of, let me rewrite it, dy I minus 2 y of I, okay. Now, the second line also similarly, I would write it dy of I plus 1. So now it's gonna predict or estimate one step ahead of time the derivative, the first derivative of y or y dot. So that is equals with current step second derivative double d y of I times delta t. We can type it as dt now, delta t, and then plus dy I. And finally, y of I plus 1, estimating the next step y is equals to the current step derivative of y, okay, multiply by d of t, and then plus current step y of I. Okay. Now what I'm going to do is that I'm going to write a simple code that include all of these three lines. Okay. So let me get to MATLAB. Now here I'm gonna first create my time vector t equals to 0 all the way to with the step size of 0.01 to 10 seconds. Then I'm going to define my input vector. I call it u, and because it's a step, it's going to be just ones with the same size as the time vector. Okay. Now the next thing that I'm going to do is that before we can start this simulation, if you take a look at this first line here, I need to know the value of the derivative of y and y for the step one. So I'm gonna just consider some initial condition here. Essentially, the initial condition y of 1 equals to 0. Also y dot of 1 equals to 0. Okay, so these are my initial condition. I'm gonna type here y of 1 equals to 0, and the derivative of y for the first part, initial condition, also 0. Then I think I'm ready to start my for loop for I equals to 1 all the way to length of t, meaning all the time increment. I'm gonna define my differential equation, use it finding difference. So double derivative of y gonna be what? Gonna be u of I, okay, plus, gonna look at here, it is u of I minus 3 y dot minus 2y. So instead of 3y, that I can type 3 minus 3 times y dot dy I minus 2 times y of I. Okay, so this is good. Then d of y I plus 1. So I'm writing this equation right here, or this equation here. So d of y I plus 1 equals to dd, or second derivative, or y double dot of I plus dy I. By the way, it's a good practice for me to define delta t. Let's say I consider this to be 0.001, 0.01 actually. And then here I just use if t. Okay. Now this is gonna be now the second derivative of y I times delta t plus the first derivative of y. And then similarly, I can define y of I plus 1 equals to the first derivative of y times d of t, okay, plus y I. Okay, so let's see. seems that everything is okay. So if everything is working fine, we should be able to actually then plot the result, in this case, t and y. Now let's save this one as example. I would say finite difference, and let's run it. Okay, so the vector y, the dimension, it says that it's not match, it's not the same. So we have 1001 for time versus y has 1002. So we can solve it a different way. We can put a minus sign here, -1, or we can plot it from 1 to and -1. Okay, so this case, it should work now. Okay, and this is the result, and as you see, it converges to 0.5, and it's similar, it's the same as this method that we have here, that also converges to 0.5. But here is a deal. This is our numerical method. Here, for instance, I used like exact analytical solution. Okay, when I'm using the inverse Laplace, this is the analytical method that I'm using. So this solution is exact. This solution using finite difference has some numerical error. Now, I can make my step times, let's say, smaller, and you would see that, sorry, bigger, and then you see that it generates some error in the system. Let's run it one more time, and you see it's not as accurate as it used to be. Now let's make it maybe 1 second and see what's going to happen. And the result is not even stable. So what you can do later on is that you can actually compare this numerical result with different step size, compare it with what? With the exact analytical solution that you obtained from inverse Laplace. And that was what? That was this equation right here. Okay. I also want to ask you guys to later on, instead of just having the step, use a sine wave, okay, and obtain the Laplace of the sine wave here and repeat the whole process. So for now, let's just put it 0.1 and run it one more time. Okay, sounds good to me. Okay, the last thing that I would like to show is that we can actually simulate the same thing using the Simulink. Now in Simulink, we can either use a transfer function to simulate this system, or we can directly simulate this differential equation in the time domain. And using a transfer function will limit us to linear system, versus if we use the differential equation directly, it can be extended to a case of nonlinear as well. So I'm gonna show both, and then you can choose which method you wanna try. Okay, if I want to simulate this block in Simulink, what I'm gonna do is that I'm gonna actually use a two integrator. Okay, so I start from y double dot, and I'm gonna integrate 2 times to obtain y, and then I'm gonna use this equation here to rebuild the second derivative based on input minus 3 times y dot minus 2 times y. So I go to my Simulink blank model, and I'm gonna navigate to the library, and from commonly used block, I'm gonna bring two integrator here. Okay. Now I am gonna get a summing junction as well, and let's make this summing junction a rectangular one, and let's have actually 3 input. Okay, and let's have the from the sources, let's bring a step response. I bring the step response here. I'm adding the step response right here, and I think this is the step time and this is the final value. These are perfectly fine. And now what I'm gonna add is that I'm gonna add from continuous or from commonly used, I can bring the gain. Okay, so I wanna have some of these. Okay. Okay. I'm gonna use this gain. Okay. Let me use another gain right here. Okay. Let me also get a scope. We can see the value of y. Now, this signal right here, let's assume that this is actually y double dot. Okay. Let's assume this is y double dot, and then we can, if this is y double dot, this would be y dot, and this would be y. Okay. So this signal is y. Now, if this is y double dot, if we take a look at this equation, y double dot is the summation of u minus 3y dot and minus 2y. Okay, so remember that. So I'm getting back to my block diagram here. So minus 3y dot, so this gain should be instead of 1 minus 3. We have minus 3 here, and then this should be minus 2. 2 here. And then I have the u as the step. So now this should be exactly the same differential equation as we want to simulate. One thing is that if you double click on the integrator, it asks for the initial condition. In this case, it is by default 0, but if you have something different, you can always update it here. Now, let me go ahead and save this one as in MATLAB example, maybe we call it what example differential equation. Okay, now let us go ahead and simulate this thing, and this is the response, and this is getting to 0.5 exactly the way that we simulated at using the M file. So we did it with Simulink now. if you want, you can actually transfer this variable to the workspace. And to do so, I'm gonna go to the blocks here. I'm gonna go to sources, sorry, sync. I'm gonna look for this block to workspace. I'm gonna grab it and bring it here. And this way, even I simulate it, the response will be transferred to workspace. Now, if I go here, actually, let me clear the workspace first of all. So the workspace is empty now. I'm gonna simulate it one more time. And this is the response you can see in the scope, but we want to have it actually in the workspace as well as we have here. If you double click on uh, this option sim out shows the time and the data. Now, based on the different version of MATLAB that you're using, these terminology for the sim out variable may be different. Okay, so just look at this block, double click and see what is the name of this variable in that particular MATLAB version. I don't know why, but MATLAB keep changing it. Anyway, so if I want to get the time, I'm gonna type time equals to out dot sim out dot time. And if I want to get the y value, I'm going to type uh, out dot sim out dot data. Okay, and then I can go ahead and plot the and y, and it should give me exactly the same graph. Okay, now I can copy these things and paste it in a separate M file and run it each time that I want to actually see the plot result, or you can copy this thing and do this nice trick. When you're here, if you look for model properties, which I would say it can be in Model Explorer, or let me see. Okay, model properties is here. If you click on model properties, if you go to the callback function, and if you go to the stop function, you can paste it here as well. Now I apply, and maybe I don't do the clear all because it will clear the workspace. That's not what I want. And then if I run it this time, what it does is that, let me close this as well. It should automatically plot the data and show the graph. Okay, you see? So we actually coded this part into the Simulink model itself, and that's interesting. Now, alternatively, because this is a linear system, I can just directly add a transfer function and it would provide the same result. So if you want to add a transfer function, you go to the library, you go to the continuous, and you just take the transfer function here. Okay. Okay, so this transfer function, we have the transfer function already here in this M file, the transfer function. So the transfer function essentially is this 1 over s squared plus 3s plus 2. So the gain of this transfer function in the numerator is just 1. Denominator would be 1, 3, 2. So I'm gonna type here 1, 3, and 2. I'm going to make it a little bit bigger so you can see this is exactly the same transfer function. I'm going to provide the same input, and I'm going to add another scope here. I'm going to run it one more time. If I click on here, and if I click on here, what you see is that actually these are the same thing. These are identical. And if you want, you can plot them on the same scope using the demux option. If you see, if you want to see like more data, if you think it's a little bit discrete, you can always go to the model simulation, model configuration parameters. Here, what you can do in the solver, you can limit the maximum step size, let's say, to this value. And then if you run it, curves should be more smooth. Okay. I guess this conclude this lecture on the simulation of dynamical system with MATLAB. Please stay tuned as I'm gonna upload more videos about dynamical system and control.